Hello and welcome to today's webinar, Identifying Emissions Reduction Pathways for Cities using UBEM.io. It's presented by Zach Brizola and also assisted by Christoph Reinhardt. My name is Alex Chapin, and I would like to welcome you all. Today's session will be recorded and is going to be available on demand. If you have any issues hearing the presentation, please message one of us via Zoom and we will help you troubleshoot. This Zoom webinar is hosted by ibpsa-usa Research Committee. Our goal is to share new ideas from research to the building simulation community. We welcome your questions, thoughts, and ideas as we continue to work towards ibpsa-usa's mission of fostering better buildings through simulation. During the webinar, you will be muted and off camera during the session, but please participate by posting your questions in the Q&A tab to the bottom of your screen and by entering any comments in the chat. By default, the chat is set to send to just the presenters, so be sure to click the arrow next to the chat and select all panelists and attendees if you want everyone to see your message. At the end of the roughly 40-minute presentation, I will unmute our audience on Zoom for a discussion with Zach. Now I'd like to introduce Zach Brizola. He's a fourth-year PhD candidate in building technology at the Massachusetts Institute of Technology and a National Science Foundation Graduate Research Fellow. He uses urban building energy modeling via UBEM.io, a tool he co-developed to help communities around the world meet their emissions reduction goals in the built environment. Through these collaborative efforts, communities define and test technology pathways that include differing levels of building retrofits, heat electrification, and renewables. His current focus is on how to equitably advance the adoption of building retrofits to attain ambitious but necessary emissions reduction goals. Please join me in welcoming Zach. And then Zach will introduce Christoph.
Hello, good afternoon, everyone. Thank you for joining. I'm really excited to be talking to you today, and I actually wanted to introduce Christoph Reinhardt, my advisor, professor at MIT and the head of the building technology program, to kind of kick us off and get us started. Christoph, do you want to come in?
I would like to if I can. Can you guys hear me? My video doesn't seem to work, but do you hear me okay?
Yep, we can hear you, Christoph.
Oh, fantastic. Welcome, everybody. And I don't want to steal the show from Zach. I'm just really excited that so many of you took the time out of your busy schedules to join us today. The idea behind this presentation is, on the one hand, of course, to just talk about where we are with urban building energy modeling today. But our ambition is, in a way, also larger. We are really hoping that UBEM is now at a state where mainstream building energy modeling practitioner can start using it as well. And we don't really care if you use our tool or the tool from LBNL or from other people, but this is really for us the beginning of a discussion where we want to talk about what can UBEM tools accomplish today. What benefit does it have for smaller cities to apply them? And ultimately, we want to work with you all on a business case. So very specifically in the state of Massachusetts, we have started to work with the DER, our local energy department. And what we would love to do is to basically secure funds so that energy modelers located in New England and Massachusetts specifically are matched up with small towns and start to do the type of analysis that Zach talked about. So if you are critical about urban building energy modeling, as you probably should be as a good modeler, then today is a good opportunity to ask us some questions, and hopefully if questions don't get answered today in the short presentation, we are happy to walk you through the tools that we have been working on and just make sure there's some action in that field. Zach, the floor is yours.
Fantastic. Thank you so much, Christoph, for joining. And thank you to everyone. I am going to share my screen. And let's get started. So as you saw in the description, we're kind of trying to take this idea of identifying emissions reduction pathways for cities using urban modeling and this tool we've been working on, UBEM.io. And so, as you're probably aware, cities around the globe are setting ambitious carbon emissions reduction targets, often to net zero by 2050, which aligns with the kind of Paris Agreement climate goals. But these cities are all coming from different places. And so I want to just kind of focus here a little bit on a use case of Oshkosh, Wisconsin. This is a city we've been working with. It's a typical Midwestern American city meant to represent any community around the country. Oshkosh has about 60,000 residents, 13,000 buildings, and there are thousands of these communities across the US. And these are the communities that need your service. Whoops, jump to slide. Many cities are already undertaking this pathway where they've done a baseline greenhouse gas emissions analysis. They know where they stand, and from there, they've set lofty emissions reduction targets, often based purely on political ambition, tying into net zero by 2050 usually. But very rarely have they actually done the math, the physics to understand what's possible in getting there. And so our whole goal here is how do they actually get to those targets in their building stock? And that's where these technology pathways comes in. These are combinations of building retrofits, energy conservation measures, in the lingo of, if you implement that across the city, how can you actually get to those goals? And this is an example of what that comes out to look like in Oshkosh, broken down by the age of their building stock, which we'll talk about later. But ultimately, and we'll dive into this more, these are different combinations of retrofits that we can then simulate across the building stock. And this should be something that's very familiar to most of you. And this work has been going on for a few years now. A number of large cities, Boston has done this, New York has done this, but most of these studies, and this study in Boston here was a we built a model at MIT, and then they built off that Boston University and Arup, for this carbon-free Boston study. But these are six-figure studies, and they require a lot of bespoke expertise that might not, you might not have in an individual firm. And as a result of the cost and the expertise required, this doesn't scale to all communities. This does not scale to the Oshkoshes of the US or other parts of the world. And yet every city has to work together to get towards their emission reduction targets if we're going to achieve everything we say we are and kind of combat climate change. And so it's critically important that these small cities are the ones that really get focused on how they also can get towards their goals. And so this is why I'm here today, and this is a lot of the work I've been doing with Christoph and others in the labs. We want to empower you, building energy modelers to help small and medium-sized cities to conduct this kind of analysis on their building stock. Right now, through UBEM.io, which I'm going to kind of intro in a minute, this analysis works for about cities under 20,000 buildings right now. And these cities, you can go larger, but when you start to ramp up the numbers to the Boston scale, you start to run into some big data issues that make it more difficult. It's computationally expensive. So that makes it harder to kind of provide a free service in this regard. But the whole goal here is there are thousands of small communities under 20,000 buildings that really need this work. And traditionally, these studies are so expensive because of the cost, because of the expertise that needs to come together. When that study of Boston was done, you have a PhD student that works for many years, for several years, building up the expertise in geographic information systems, in the goals of the city and how it stands, and in the actual composition of the building stock. And so what we've done with UBEM.io is break this down into the key roles that all come together. And as long as those folks bring in their individual expertise and work together through the process we've set up, it can be, the process can be defined to their traditional work. And so this involves a sustainability champion in a city. That might be a role that someone is paid for to do their modeling work. or to do their kind of sustainability championing work, working across the city, not just in buildings, in transport, whatever, but they understand the city goals, they understand the city government and what's possible, how to get money. But they probably don't have a very good understanding of what it takes to do a building energy model. There's a GIS manager. These exist across the spectrum of cities because this is how taxes are done. The footprints of your buildings, the square footage, this kind of information, their age, helps the cities evaluate the value of your buildings. And so they pay someone to make sure that data set is good, because I don't want to pay more for taxes than I have to. And so I'm going to fight if I think you're saying my building's too big. And as a city, they want the building to be the right size as well, so that they get the most tax revenue. And so this position exists in Boston, but we've worked in a small county in Vermont that exists at the county level in places because, again, they still have this need. And the same with the sustainability champion. Even if they're not on the city staff, it's a volunteer, it's a community group that cares about this, somebody in the community that wants to see the city working towards their goals. And then finally, there's the energy modeler. You've been doing energy modeling at the individual building level. You know how to do that kind of modeling. And our whole goal here is to get you from that individual scale up to working kind of at a city scale. So to do this, we've built the UBEM.io web app. We've tested this in case studies in 20 cities around the world, 8 of them in North America. And our goal is to really help you grow the impact of UBEM, specifically in North America, the US especially, for reasons we can discuss a little bit later. This kind of US-Canada focus is a little bit easier, but with more work, it could be done elsewhere as well. And I just also want to note, in addition to the recording being made of this presentation as a reference, pretty much all this information is coming directly from the website. We have this all documented out so that you can go through step by step and get guidance along the process. And so turning to that actual process, one of the key innovations here has been really defining the roles and what each one of them does. And so this is, UBEM.io is a free service that we want you to use. And if there's anything that isn't clear as you go through this process, let us know, because we want you to succeed. And these steps are meant to make it really clear who does what. So the first step, the feasibility check, that's before they even hire a building energy modeler, the folks in the city meet and say, do we have the right data to get this done? What are our goals? What are we trying to get out of this? Then once they've done that, and maybe they're applying to a foundation to get a grant to support the building energy modelers, or we're working with, in Massachusetts, for example, the Department of Energy Resources to get funding for that, finding the resources to make this study happen. Once that's set up, they meet with you, they bring you in and define a project scope. This is something you're familiar with on any project. What are the goals? What's the data we have? How are we going to set this up? Then the GIS manager goes and does their thing, prepares the GIS data, maybe checks in with you to make sure there's agreement on a few things. But for the most part, they handle all that data, and they can upload that data to the website where we run some quick checks to make sure that it's working the way we expect it to before you even get it. Then in step 4, you get that data from the GIS manager, basically all set. You're going to build the baseline model, and kind of from the rest of this, I'm going to actually walk you through it each step along the way and draw the parallels back to individual building energy modeling, as well as kind of moving forward. So first, this building the baseline model. This is what you've seen once you've actually been handed the file from the GIS manager. It shows you a couple of the key fields and make sure that there's no errors. The image you see right now is a small test case in Vermont. That's about 90 buildings. When it gets really large, we stop displaying an image just because of computational resources, but the key data checking is still happening. And so what you're seeing here is all of our models, instead of in an individual building energy model where you might draw from a plan, or you might draw from a CAD model, or you might actually, like if you're modeling retrofits, go onto Google Street View and draw it by hand. We pull in this geographic data, which has the building footprints, and then extrude those up to the height based on 2.5D. And so that's kind of getting up to the volumetric equivalent of the building. And then beyond that, there's some other key things that we do to document those buildings and create them in our model. That's things like we then kind of are breaking those building stocks in, those other categories you saw, or how do you break down the building stock? And this is because instead of a single building, we're talking about collections of buildings that are similar in their construction. And so things that we often use are use case. Is it residential? Is it commercial office buildings or something, or schools? And then what's the year built or the year last renovated? Because that really defines how it's constructed. And you know this as well. When you go into a 1900 farmhouse, it's going to be very different from a building built in 1995. And so this is the kind of knowledge that you already start to have. And it's working with that GIS manager to understand how you break down the building stock. If you have fuel type data, which talks about what heating systems currently in the building, like that can get integrated, or something else, other information that they might have that's relevant. You have that expertise to tell them this is, they tell you what they have and you can ask for what you want. And so, kind of the key ingredients that you're all familiar with in a building energy model. You've got weather data, you've got your geometry, and then you've got a bunch of non-geometric building and occupant parameters. They describe the construction of that building, the HVAC systems. They describe the equipment and lighting loads and the schedules that are associated with that. You've spent hours perfecting that for buildings as you're working through this to define for that one building. In urban building energy modeling, you define it for an archetype. So again, back to this idea of segmenting the building stock. What are all the buildings that have similar construction types and similar use cases? Because that's how you're defining it all. And instead of simulating one building, you simulate a bunch at the same time. And in our case, we run this through UMI, which is a plugin we've developed in the lab for Rhino. We'll talk about this a little later. But it's ultimately calling Energy Plus at the end of the day, as many of you are probably familiar with in your kind of current work. And we've now put a lot of this in the cloud, right? And the simulations are happening on a computer, but kind of here, as we're moving forward, we've now split up our archetypes, split up our buildings into these archetypes that we call them. You define how much window there is, the window to wall ratio based on that archetype, and then you assign templates. And these templates get into that information about those different types of buildings. And you don't have to build this from scratch. We've provided a lot of this for you using Department of Energy resources, which is why this works the best in the US and Canada. Is that the US Department of Energy, NREL, PNNL have put a lot of effort into defining these commercial reference buildings of these different vintages. And on the residential side, some residential prototype buildings, as well as res stock data that we're incorporating right now to basically help you split out the construction, the loads based on climate zone and vintage, and maybe heating fuel, so that you don't have to do a lot of work. You can start with one of these templates and then make the tweaks that might be different in your area compared to what's in the standard prototype. And so this is all this idea of, you start with a standard building, make the tweaks that you might want for your area. And everything we do when we pull these in, we normalize it. So it's a per square meter basis. And so everything that might have applied to a single building now applies to all the buildings of that type. And so you have to keep in mind at this step that you're never going to get that exact, equipment power density spot on, because there's a whole range of values across all the buildings of that type. But as long as we get a good basis here, we're in the right place. And that's kind of all this is about, is focusing on high level questions around strategies for across a whole city. And so that's the whole idea, is to provide you with that data that you can adjust if needed. Kind of thinking again globally, if you're joining us and you work primarily outside of the US or Canada, thank you. We're glad you're here. There are workflows to do this outside of the US. We've had some success in translating this tabular database in Europe, which the countries have done the archetyping work of defining what the different categories of buildings are and what the kind of profiles of construction are. but there is some kind of more manual and tedious work to get that into the simulation formats we need. If you want to learn more, we can point you to the right resources. We wrote this paper about how to do that and proving it out in Ireland. We have Irish and Portuguese building stocks kind of readily available to share if you want it. But for other countries, you might have to do a little bit more legwork to really define it. But it can be done around the world. So now that we've kind of figured out all these different pieces, what does this actually look like? So this is Boston, and just kind of zooming in, once we've found those footprints, we're extruding them up to their height. We have a sense of the floor-to-floor height, although we generally simulate the building. And we've applied a window-to-wall ratio. We understand the radiation going on and shading from all the different buildings. And then finally, we run Energy Plus. And instead of just doing this for one building, we're looking across all the buildings in our area. And so, when we get to actually running the baseline UBEM, we've built this whole model for you on the website. And then when you get to the end of the workflow, you download the file for simulation. And basically, you open up the file in Rhino. And Rhino has a free trial if you want to get started just to play around with this. That's the kind of piece you have to download. And then UMI, which is our plugin, is freely available. And we link to both of these on the website as well at this stage. But you basically download the file, open it up in UMI once it's installed, and make 2 clicks and go. And so we have this batch mode. If you're working on a laptop, you can run it 50 buildings at a time, and that will work on a laptop. At a city scale, it might take you a long time, but on a big desktop, or if you're doing this elsewhere through the cloud, we can, on a big desktop, I can run 20,000 buildings in something like 6 or 8 hours. And so it's definitely not immediate, but it's a lot faster than if you're running 20,000 buildings in Energy Plus one at a time. And one of the ways that we do this is we've developed this shoeboxer method, and my predecessors in the lab specifically, that rather than run a full multi-zone model, we look at this 2-zone shoebox on a bunch of representative areas in the building stock, and something like you might do for building level facade studies. So, we've run this, we basically have sped this up and shown, if you want to read more in this paper, this can work. It's pretty accurate, and it helps us kind of tackle these really big buildings with reasonable computing resources. So once you've done all that, this is the kind of thing you might get, is what the energy consumption is across all the buildings. And it's important to note, because of this shoebox method, you can't actually go to 100 South Main Street and say, what's the energy use of this specific building, and say that that's going to be spot on. There's way too much kind of stochasticity in this, and changes at the individual building level based on occupancy and all the stuff that you as an individual building energy modeler have spent, and myself too, in previous work, spent time trying to figure out how good is this, and tweaking little parameters to get it just to line up. You don't have to do that, because we're caring about across all the buildings of that archetype, hundreds at a minimum, how are we in comparison? And so this is the kind of outputs that we get. And so you might be wondering, how well does this actually work? We spend so much time at the individual level trying to get it to line up. This is some data from Oshkosh, based on their 2019 utility data. And when we did the modeling, we came within about 5% across the whole city in terms of energy use. And pretty good alignment between heating versus equipment. And you don't just have to take our word from us in this one, in the Oshkosh case study. There's been a bunch of different simulation studies across around the world with this kind of work. And in general, they've been finding that these archetype level simulations are pretty good at getting the within 15%, the ASHRAE 14 max allowable error for this kind of modeling. And you can see that even the ones that aren't quite there are pretty close. And for a policymaker, that kind of area, move in this direction, and we're getting to you within 10-15%. That's really all the information that we need. These are the studies we are aware of. There are definitely more out there. But generally, they all agree that we're in a good enough spot to make decisions at this archetype level. There's definitely room for improvement there around like tying this back to the census and actual people in the space and all sorts of other things. Like, we know we're not perfect, but we're just trying to get a good, good magnitude of in the right ballpark. So once you've got a baseline that you're really happy with, that's where building upgrades come in. This is the kind of thing that we spend a lot of time about for the individual building, but also I can, rattle them off the back of my head because most of them matter. You use similar ones for similar types of buildings. And so that same knowledge kind of rolls over to this urban scale modeling work. You're going to come in and figure out, what's the insulation levels, and might test a few different things, but do this not just for one building, but for all the buildings of that type. And this is, again, where those archetype matters. If it's concrete masonry unit walls in that building archetype, you're going to have very different strategies than you might have for wood frame single family housing. And that's where your knowledge gets to shine. And that's what you bring to the table here, is defining the right kinds of retrofits that could actually feasibly be done in most of these buildings. And so, this is kind of over and above that. And so the way we've implemented this on the website is, if any of you are familiar with Open Studio measures, it's the same kind of idea. We've defined a bunch of generic measures that touch on most of the different end uses and kind of common upgrades that you can define, things like equipment. And so you go in, and for each of the different scenarios, you can define the different upgrades. And if there's any on there, if there are any retrofits that as you go through this and you're using it and you're like, oh, we'd like to do X, and it's not on there, we can make that available really easily. That's a quick thing that we can change to make sure that we're providing you, the access into the things you're curious about. And we kind of have some more expert level ways to get in and describe how you are changing things. But we've just made this GUI that makes it kind of easy to do the common building upgrades and adjust the specific values to the ones you're, focusing on. So bringing it back to our case study in Oshkosh, what are the upgrades that we wanted to do there? And so we have these two different, energy conservation measure packages that we put together and looked at kind of in the pre and post 1980 to 2004 and before 1980 building stock, and define these mostly based on the Energy Star for homes, new construction, but like a lot of the retrofits happen in this direction as well. And so, what you're seeing here is fairly good in high insulation levels, maybe not reaching passive house, but, pretty serious projects. And that's actually what it took to get towards their goals. And that was, eye-opening to Oshkosh themselves. And we'll talk about this a little bit more, is that, to actually achieve these goals, the retrofits are really serious. And that, led to a lot of really good conversations, which is exactly what we're trying to do here, is influence the policymakers, tell them what they need to do. And so, the second measure focused really on electrification, air source heat pump water heater, rooftop PV, the kind of heat electrification side of it that may not make sense right now on the grid, depending on where you are, but definitely is key towards, as we get a decarbonized grid, getting the city towards its goals. And so once you've run the scenarios, and you, again, with these upgrades, you do the same thing, download the files, run them on Rhino with UMI, or again, we're happy to use a different tool. If you want to work on something else, work in some other scenario, we can, we're interested to learn about that. You don't have to use UMI, kind of build out from that. So just to like quick, this is the same thing I showed you before in Oshkosh, baseline 2 upgrades, but the kind of operational energy EUIs. You can upload a bunch of different scenarios, play with it, run with the different strategies, change the future grid emissions, all sorts of different kind of knobs and levers you can pull inside there beyond just like what you're uploading from the scenarios. And this is where you're checking, like, does this make sense? Do these align with what I'm expecting? And then once you've done that, the city doesn't actually, and the decision makers in the city, they don't really think about EUI very much. That's a building energy modeler thing. They think about what's my carbon emissions? Am I going to get to my targets? And so you can see in the green lines, the Oshkosh targets overlaid here. And so what you see is that it really did take that electrification measures on top of all the efficiency work to get towards their goals. And so that the combination of efficiency, electrification, and rooftop PV across 50% of their rooftops actually just nudges them beneath their goals. And that's on purpose. These retrofits were designed to be feasible and also get them there without, maybe pushing them more than they needed to. So finding that right cost benefit analysis. And that's exactly what, you might do at an individual scale. And now we're trying to do that for the whole city. And so this is ultimately this clear technology pathway analysis. If we combine all these different retrofits applied to all the buildings across Oshkosh, this is where we get. And again, Oshkosh is one city. We need to do this for a lot of cities. And ultimately then, where you come a little bit into the picture is present your findings to the sustainability manager, show them that previous slide, and then work with them and so that they can then do the kind of communication out to the community and other people relevant in the policymaking sphere about how they're going to get towards these goals. And so, this is where your job ends. You don't have to do this kind of engagement work, but this is just an example of what we did in Oshkosh, where we defined in plain terms, not ECMs, energy retrofit or energy retrofit and heat pump and solar for, what it's going to take, what the costs are going to be, the emissions reductions, things like that. And, there's definitely a lot more information that has to happen here of like, how do we actually get to these goals? And there's more work. But again, as an energy modeler, your role is done. This is where the city, the policymakers start to come in. And if you get to this point, though, and you're working with cities and they don't know what to do, or they're unclear, you need more information, like, let us know the challenges you're facing here. We want to learn more. We want to make this better. Some of my work on adoption starts to come in at this point in the process. So we're always trying to push this forward more. So maybe just wrapping up here a little bit. Why do we actually need this in every city? What's the reason we're giving this? I want to talk to you about this today. Why do we build this and say, all these communities around the US need this? Well, every city is a little bit different. And regionally, there might be a lot of similarities, but the building stocks themselves are very different. And these are all based on the volumetric kind of energy use of these cities. And so it's going to matter a lot as you go to new places, how you're going to get to their goals. And so we did this study. We've worked in 20 cities, but here we kind of looked at 8 across the world. And the goals, existing conditions, strategies they had, and the results we get out of these studies varied immensely across them. Many of the cities that we worked in couldn't reach the goals they've set, but the combinations of strategies to get there really varies widely based on the building stock, based on the existing policies they have, based on their energy costs and emissions. And so I just want to highlight 2 of these. Florianopolis in Brazil, it's a hot climate there. And they basically, almost all their energy comes from cooling. And so this is kind of the emission side of their technology pathways. And basically all their emissions right now are coming from electricity use, and they need to figure out how to decarbonize that. And in getting there, in order to not spike peak demand, energy efficiency plays a key part of that. And so that's where these shallow and deep retrofits come in. And then if they do those deep retrofits and they decarbonize the grid through a lot of rooftop solar potential that we found, as well as kind of bigger projects, they can actually get to their goals. Middlebury, Vermont's a small town in Vermont. They are predominantly a clean power grid, a lot of hydro, but almost all the heating happens through heating fuels. And so that's, leading to high carbon intensity amongst the heating emissions. And so for them to actually get to their goals, that kind of efficiency around the buildings and then decarbonizing and then electrification to take advantage of that decarbonized electricity is what it's going to take. And you can see here that there is still remaining emissions because in the considerations here, for example, heat pump water heaters were not very popular when we started talking to folks there because they hadn't been shown a few years ago to really work in Vermont. And so they didn't get implemented. And we showed how much of an issue that can be for emissions, among other things around some other end uses. So this really shows the dichotomy of what happens and why these matter so much. You can think about across the country, there's great differences around what each city is going to actually have to do. So thank you very much for joining us today. Our goal here is for you to use your building energy modeling knowledge to be an agent of change in your community and communities across the country. Visit ubem.io today, give it a try. Let us know if you have questions, run into issues. Our goal is it's self-explanatory, but if there's something that's missing, please let us know. We have some improvements coming over the summer where we've implemented some accounting systems, basically that let you hand non-proprietary data over between the 3 people involved through the website without having to, Dropbox or email files. But the key functionalities are all there right now. And our hope, we're still seeding some of these templates to upload based on the kind of res stock data, but the commercial side is there right now. Most of it is there, and we want you to really engage and learn from it. So with that, thank you very much, and I look forward to your questions.
Thank you, Zach and Christoph, for starting us out. We actually have a few questions already. Most have been put into the Q&A panel. I think there were a few that were asked in the chat and didn't get transferred over. Can you see the Q&A questions, or do you want me to read them?
Yeah, I can see them here. I'll just start going down the list.
Great.
So someone asked, is ubem.io applicable at the university or institutional campus scale as well? It depends is my answer. When you're down at a campus scale, the archetypes are, you maybe don't have enough buildings to say that you're doing a good job that well. If you only have a few buildings per archetype, it doesn't work. Now, if you're talking about a campus that has a couple hundred buildings that are very similar, I think that we would say that we're comfortable with that. But if you're really trying to drill down at the campus scale, you need to do calibration work, just like you might have to do in an individual model, where you get measured utility data and then adjust some of the parameters to really line up. So that's a little bit more work and not really built into what we do now, but you very well could build a process around that, and where you kind of take the data through and then adjust parameters as you need to line up. But because we're not simulating full models, I'd say that we can't say if you've got 50 buildings and they're all a little bit different, they don't fall under the same archetype. It's really not built for that right now. So the next question is, what considerations are made to include load profile variability, thinking about unreasonable coincident peaks impacting results? This is a great question. Right now, honestly, most urban models are cities of robots. Every light turns on at the same time, and and your dishwasher comes on at different time or the same time. There are some ways to change that. There's been a lot of research in the field to do that. You can make different archetypes that have different schedules. So you can absolutely do that and say, oh, this is my and we're starting to do this. This is like my retired couple, especially in a residential example, you might have a retired individuals, and they are kind of more constant use throughout the day versus a young student, a student or a young working family that is gone for the middle of the day. And so you can build that into an archetype. So you don't just have to define it on fuel types, you can define it on the occupants themselves, if you're really trying to get at things like peak load. But again, this is where we're really, for the most part, in these focused on carbon emission reductions for kind of policymakers at the city scale. And so the fact that they all come on and off at the same time doesn't matter that much when at the end of the year, the kind of total consumption is the same, whether they come on at 9 and turn off at 5, or they come on at noon and turn off at 3 or something like that. I don't know, I'm making some numbers up.
Quick question related to that, Zach.
Yeah.
That sort of assumes that you're looking at grid emissions from a annual basis. I know that there are some people who are now trying to look at hourly grid emissions and when power, electricity is actually being used throughout the day, because you may have different sources, like a grid may have PV during the day, but coal at night or something like that. So is that something that you guys might look into eventually, where you might care about wind during the day and like peak demand? And
Yeah, I mean, so this is a great question. We use we pull right now from Cambium, which is the National Renewable Energy Lab's tool for like grid emissions, both the like projections out to the future. If you want it, we can you can seed it with that. Or right now we just kind of look up the like current emissions factors that is expected. But you definitely could start to get into, if you wanted to go into this, and we have an interesting, and I think it's linked on the website, this kind of different use cases for urban building energy modeling. And what you're starting to talk about is what we call a use case 3, which is all about this like buildings to grid analysis of like, how does the grid and the buildings interact? Right now, our simulation fidelity, I mean, we're running Energy Plus, so it's doing its 15-minute or hourly simulations. But ultimately, we're reporting out at a monthly data, at a monthly increments. And when you start to shift towards hourly, the file size just starts to go through the roof. And so one of the things, and I didn't say this exactly directly, but you may have got the gist. Our goal here is to keep the cost of these studies low, because this is not, cities don't have lots of money to do this, but they need this kind of analysis. So we've focused wherever we can on simplifying to keep it, easy to do. And so that, and from a, firm perspective, if you're working on this as a modeler, it's more of a, let's do this a bunch of times and build a business that way, rather than, oh, we're going to make a lot of money off one study. And, there's so much demand for this that we think that's a really valuable proposition. But the kind of key piece to maybe go in directly to answer your question is, you can do that and download the kind of, get it out at UMI can spit out hourly results. You could go and do that. The file sizes go up exponentially. The complications get more, it gets more complicated. It can be done, absolutely. And we're definitely looking at that area actively. I think we'll have a paper coming out about some of that work actually pretty soon. So we're definitely in that area and thinking about it, because it does, especially when you start to get these variations with PV during the day and not at night, it does matter. And, as a lot of places are starting to think about 24/7 carbon-free electricity, it matters a lot too. So absolutely, it's important for a lot of the use cases we're talking about right now. Simplification has been important. Great, I'll keep going. How is shading from trees handled? This has a big impact on energy use in single family houses and also leads to big variations from airport weather data files. Great question. So a couple of things. You can pull trees into the model. We actually, on ubem.io, I didn't show it. One of the layers you can toggle on is we pull from OpenStreetMap, the trees layer. That data set is not that big, but it does exist in some places, and they would be handled as a shading object. We don't necessarily, so if that data goes in, it'll get, brought into the simulation and used. But again, that we sometimes don't have all that information at the city scale. And, that's definitely where some of that variation comes into effect, right? And this is where we say, well, we're just not, we're not aiming for perfection, unfortunately. We're aiming for pretty good. And so the question, though, to the latter part of that question on, airport weather data files versus, an urban heat island effect, kind of accounting for it in a city or even, in a more suburban place, that's definitely, we seed you with the closest weather file, which is usually the airport. But, that's up to you. If you think there's a better weather file, or you can go in and want to do an urban heat island effect analysis on the weather file, or do it for, being out in the suburbs, like that's absolutely something that you can go in and change the weather file, morph it to whatever you want it to be, you think is best for that area. Absolutely, like you have the control over that. Again, the three kind of key parameters going in, the weather, the geometry, and the non-geometric properties, like each one of those, you can twist the knobs on that you see as you see fit. hopefully that somewhat answers your question. Next question here is the level of information about the existing buildings required for decent results. This is a three-parter, so I'll go one at a time. These are, 2.5D models, and we found pretty good luck with that. We're losing we try and, the height should be generally incorporates some of the full volumetric. So if it's got a pitched roof, we're probably getting somewhere in the middle of the roof height to get the full volume of the building. And so the kind of volume across the city is still getting accurately represented. And so when you're talking about heat flows, building energy modeling heat flows, we're still doing a pretty good job. We don't need, detailed information about all the buildings. That window to wall ratio is definitely a big, is a factor, how much window area there is. That's something, again, where these prototype buildings have good references, and also kind of pulling in your local knowledge of the community. And that's one of the big important things here, where we want to engage lots of different firms, is your community best. You've been modeling and working on buildings in these communities, so you understand like generally what they look like. And so that's kind of our goal there. We've seen kind of differing results. It does vary, but that's the information level that we're trying to get in. Again, knowing that there's a lot of individual variation at the individual building level, but across a whole archetype for the policymakers and the sustainability folks, you're doing a pretty good job. This question kind of also asked, the second part asked about campus master planning. I kind of answered that, and they mentioned, we did a model on the MIT campus. That paper is available. If you're interested, I'm happy to share it with you. You saw my email earlier, but that is, that's where that calibration comes in, because you're trying to dive a little bit deeper and tweak some of those knobs to really get the individual buildings set up. But at least you build the model really quickly through our kind of workflow, and then beyond there, you'd have to kind of set up some more individual tweaks to get this to work. The question about the building, there's a question about building owner that has a portfolio of multiple properties with a wide geographical distribution. We have played with this. It's not in production format right now. I mean, we've definitely looked into this. I spent a while looking at it, and it's definitely doable. The whole, kind of this workflow will work for that, but we're not there yet in terms of like making it freely available to everyone on the internet and say like this, we're happy with this to work. So stay tuned is what I'll say to that. Yeah, okay, lots of questions coming in. This is great. A question on the pros and cons compared to other tools on UBEM, about UBEM.io. Maybe and someone else is asking kind of about ResDoc and Comstock. The two things, there are a lot of tools out there. What our goal is with this tool is focused on policymakers at the city level, which we think is something that not a lot of other tools are doing a lot of work, because ResDoc, Comstock are really great tools, and we actually use a lot of their kind of the data on what the kind of characteristics of the buildings are to seed into our templates. So that data is feeding directly into what we apply, but we're applying this kind of volumetric study based on the actual volume and physics of energy flows in the buildings at that city scale, which is a little bit finer scale than the kind of ResDoc Comstock analysis that's going on, where they're simulating these representative buildings. And the representative buildings make it tractable for the city, for the national or state scale. But for an individual city, especially these smaller communities where you might only have a handful of representative buildings in it, we think that this kind of geometric work really makes a difference for talking about what the people care about. And the fact that you can see, oh, this is my community, this is my layout of the actual buildings going on, we think that's really important. And one of the big pros of the work we're doing, it really ties to the individual community and their buildings, their decisions, what they can do to the exact buildings that they see. Again, when you start to get to some of these bigger, there's definitely, other ways to go about it. There are other kind of urban modeling tools that we would love to, if you use this a lot and you're gung-ho about, this pipeline makes it easier to build a model, but you want to run the simulation somewhere else, let's talk about it. Like maybe we can find a way to make it so that you can do that. Because our goal is really to accelerate the use of this kind of modeling. Let's see. Somebody else asked that they kind of use Dragonfly and Grasshopper to create an urban energy model. And if they can calculate the carbon emissions using UBEM.io. It's not set up for that right now. We take in these UMI files that we build, but it would not be hard if you really wanted to rerun it, say in UMI. If you've already got it in Rhino, you could massage it that way. But you also probably started with a GIS file that you could just as easily run through the pipeline again. Again, these are the kind of things, like if that's the preferred modeling pathway, it wouldn't be hard to go about and do this, and we're open to collaborations in that regard. But right now it's not set up for that. Someone is asking if it can be used to manage a city with very different buildings, social houses, multifamily. Absolutely. That's exactly what UBEM.io was built for. I showed, Oshkosh is very homogeneous because a lot of American cities are very homogeneous, and we focused there. You maybe got it. They were curious only about their residential buildings. They have a small downtown core that was mostly the kind of University of Wisconsin Oshkosh that has its own stuff going on. So we didn't even touch that. We didn't want to overlap with them. So they were almost all single family homes or duplexes, which we just basically modeled as single family homes. And so, but in a lot of these other cities, like Singapore has a lot of high-rise housing stock. We've modeled places where there's a mix. And actually Brazil was a good example. There were some single or two-story restaurants, a bunch of high rises. Those templates cross kind of all the different categories. I could go back to the slide if we really want, but restaurants, high-rise apartment buildings, offices, hotels, we've got all that information in there. And you just have to break down the building stock, or the GIS manager just has to break down the building stock, because as we all know, there is a big difference between the equipment loads in an office building versus a house versus a restaurant. And maybe as a quick anecdote here, since I'm talking about it, when we were working in Brazil in Florianopolis, one of the things that we were able to bring to the table to them was we quantified just how much the equipment loads across all this restaurants in this downtown core were contributing towards their emissions, and how putting in electrified induction cooking equipment both reduced all the heat loads that were going in that they then had to air condition away, and how better air conditioners had reduced emissions. And so they got this win-win. And it wasn't just, oh, we got a win-win in one building. It was, we can get this win-win across all these buildings. And they saw the actual impact on their emissions across a section of the city because of this modeling work that led them to put in a policy of how, of starting to do the work on how can we require restaurants and other big consumers of this to kind of work towards electrification to reduce and have more efficient appliances, and therefore need less energy for cooling. So that's kind of the outcomes that come out of some of this work. So yeah, so someone asked a question about, completing a lot of these surveys, about kind of my idea here of trying to get this more towards something you can do faster rather than, hundreds of thousands of dollars for an individual city. Our hope actually is to start, is that you play around a little bit and give us some feedback on what you think. When I build an Oshkosh, that model of Oshkosh, the first time doing it research, very research intensive, took a lot of hours. But as now we've started to build cities around, it takes me, an hour or so to prepare all the files, a bunch of, an hour to click through all the workflows in the website, and then a bunch of downtime that I'm not doing. It's just running on my computer to run it. But even then, all of Oshkosh with the 3 scenarios is like a 2-day process. And then a couple of hours of trying out some of the different upgrades and things like that to get them to their goals. And then a couple of hours presenting it. The whole point here is you shouldn't be taking much more time than you might be doing in a fairly early stage design work on a new single building or two, because you do have to understand like what you're going to do to each of those buildings, and that takes some knowledge and time into it. I don't have specific figures about, per square foot or per acre, because it actually scales more. It scales better than that, because it doesn't, it's not per square foot or acre of city. The bigger the city, the less, in theory, some of the less cost it should have, until you hit the point at which like you need to run this on a lot of computers or a server, because you just can't handle that all on a desktop. And so, the small city, 1,000 buildings or a 5,000 building, 5,000 person, 500, 1,000 building city versus 20,000 should be all actually about the same. And we're focusing on that because of this, our goal here, that's a good spot for kind of cost, being similar in effort level.
Zach, we need to kind of try to wrap up a little bit because I have a few things to say at the end. So
yeah, absolutely. So I'm going to just put in the chat to everybody my email, because if you've got follow-ups, I see one of those, a couple of these. But everyone, great. Thank you so much. I'm so glad to have been able to talk today. And I'm glad for IBPSA for this opportunity to speak to everyone.
yeah, this was great. I actually enjoyed this a lot myself as well. Okay, so now I'm going to go through my spiel that we do at the end here. Thank you everyone for joining our webinar today from the Research Committee of ibpsa-usa. I'm going to put a few links in the chat unless someone else who's on helps me, but I'll work on this here to go kind of quickly. So we got, this is an email. Zach put his email in first as the MIT one. There's a research ibpsa.us email. You can send emails to that if you are interested in helping out with the research committee. And one of the things that the research committee works on is putting on these webinars like the one today. And here's another link that will take you to, looks like someone's also helping me with that. This will take you to the form if you're interested in being contacted, so that we can invite you to our meetings that we have where we plan these. And if you're watching on YouTube, don't forget to like and subscribe to the YouTube channel. I also want to mention that next month on May 25th, we're going to have Zoltan Nagy, I believe it's pronounced. He's going to present on designing grid interactive smart communities using CityLearn. That sounds like it's kind of similar to what we learned today. So if you liked today, you should come back for that. And I'm going to put the link to sign up for that one in the chat as well. And that's it. So I want to thank you all again, and I hope you have a wonderful rest of your day.